In this video, let's review the major concepts and skills using Newton's laws. Specifically, we're going to look at physical system all in variables and go through the whole process and remind you how to do everything and come up with a final result and then interpret the result. All right, so let's get started. So the heart of the first law is that velocity is constant. And that's only two possible ideas. The object's not moving at all, or the object's moving at a constant speed in a straight line. And this occurs unless any net external force acts upon the object. So here's a block. It could be sliding across the ground forever and ever and ever at a constant velocity, assuming there's no friction here. And this would absolutely not require any force to occur at all. In fact, if we were to draw a free body diagram, you'd have the force of gravity here, and then you'd have the normal force, and they'd be balanced. And the object would be coasting along to the right at a constant velocity. Of course, in order to get the object in motion to begin with from a state of rest, you would have had to have pushed on the object with an unbalanced force. But at this particular snapshot in time, we don't care about the past. We only care about this moment in time. And the forces are balanced, and we have constant velocity motion. All right, so that's a key idea of the first law. An object can definitely be moving let me back up. An object can definitely be moving while having forces exerted on it and having a constant velocity as long as those forces are balancing out, as you can see here. All right. Next, with the second law, the absolute main core idea is that accelerations are caused by net forces exerted on objects. We change the velocity of an object when there is a net external force exerted upon it. And that acceleration is directly proportional to the net force, and it's inversely proportional to the object's mass. Importantly, accelerations do not cause forces to be exerted on objects. It's the other way around. However, when we start working through problems, we typically like to write Newton's second law in this way, because we like to add up all the forces, say in the horizontal direction on the left, and then that'll equal the object's mass times whatever its horizontal acceleration is over here on the right. So in this way, we can construct some equations and then use those equations, which we'll see in a little bit in another great example problem. Also remember that force is a vector, and you can also calculate the net amount of force through vector addition if you have all of the force vectors. We've seen that before, but usually when working through problems in physical scenarios, we're dealing in component form, as we'll see. The third law is also very important. It's also pretty easy to remember, this idea of equal and opposite forces, but we need to go a little bit more deeper than just that. And we'll say that when object A applies a force on object B applies a force back on object A that is equal in magnitude but opposite in direction. There's always a pair of forces, and there's always two objects interacting. Couple examples. You could drive in a car and maybe there's like a bug here and there's going to be a collision with this little bug in the car. And it's very important that you realize that the force that the bug experiences from the car is absolutely identical in magnitude or size from the force that the bug exerts back on the car. Force of the car on the bug is the force of the bug back on the car. Surprisingly, even though they have dramatically different masses. So we'll write that out. Force of car on bug is equal to minus the force of bug on car. To explain why the car survives and the bug doesn't requires you to think about Newton's second law. And so if we write that down, we realize hopefully very quickly that if we have the same amount of force being exerted on both things, but it's the mass down here that's changing, we can see that with a very small mass from the bug's mass is very tiny, then we're going to get a very large acceleration to be produced, assuming that this net force is the same, which it is because of Newton's third law. All right, so that was that major idea that we saw with the third law. A couple other examples. If you have a book on a table, then what is the third law pair, or what are the two objects interacting? What are the pair forces? Don't overcomplicate it. You're just looking at the two objects, and once you identified physically the two objects, you're done. we would have the force of the book on table, and then you'd have the force of the table back on the book. And that's it. That would be the third law pair. And then over here on the right, 50 newtons is pushing on A. However, 50 newtons is definitely not pushing on object B. It's not touching object B, assuming that's a contact force over there. However, if we zoom in on this interaction between the surfaces between A and B, we can clearly see that A is touching B and B is touching A, and there's going to be a force of A on B and B on A. And those forces will be identical in their magnitude, but just opposite in their directions. All right, we won't draw those out here, but we've seen that before with two blocks, for example. Now at this point, we've done enough analysis to where you should be able to solve a problem like this. So we have an inclined plane with two blocks, a pulley system here, and you can see the plane is at some angle. There's no friction. I'd like you to pause the video and spend some serious time to determine the acceleration of the system in terms of these four variables. So the only thing that I am allowing to have in your answer at the end of this problem will be, some combination of those four variables. All right, great test of understanding to see if you can do the whole process in variables, and it also kind of combines a lot of the more complex physical systems that we've seen, such as the Atwood machine and an inclined plane, in a great problem. All right, so pause the video and go off and kind of work this out on paper, and then come back and you get some feedback on how you did as we will go over all the steps that you need to be able to do in order to show the ability to analyze physical systems on your own. All right, go ahead, pause the video and give it a shot. All right, so first, I've kind of redrawn the picture and I've put some boxes around both of my objects. Then I'm going to focus in on identifying the forces first. So I can see over here on the hanging mass, I'm going to have a tension force pulling up and a gravitational force pulling down while this system is doing whatever it's doing. Regardless of if the mass is going up or down, there's going to be those two forces and they're going to be in those directions. Likewise over here, with mass A, ropes can only pull. So this rope is always going to be pulling with a force up the ramp. And the gravitational force, well, it'll always be straight down, but there will always be a component of it in this parallel to the ramp, pulling down parallel to the ramp. Gravity's not going to flip its direction and all of a sudden try to go up the ramp. And then finally, we've got the normal force that's always going to be perpendicularly pointing up the ramp like that. So we can see with a quick identification of all the forces here on both of the objects, they're always going to be in the same direction. And their directions of the forces aren't going to be changing, regardless of if the system rotates this way, clockwise, or if it rotates the other way, counterclockwise. You could imagine that this system could either be balanced, where there's just enough mass on both sides with the correct angle, so it just kind of like hangs there motionless. Or you can imagine a situation where it starts to rotate this way, if the angle was kind of shallow, or if the angle was really steep, it could rotate around the other way. It just all kind of depends on what that angle is. So we'll kind of keep that in the back of our minds, and maybe that'll come out of our final solution as well. We'll see. All right, so let's set it up. I've written down the second law now, and I've also put our coordinate system here. Actually, let's finalize our coordinate system. We'll say this way is positive. So down here would be positive, up would be negative. And likewise, up the ramp is positive, down the ramp is negative. And I'm just going to assume right now for my visualization that the system is rotating clockwise. So the hanging mass is going down vertically over here. All right, some of the forces on object B in the vertical direction. Well, we have tension that's pulling up and gravity pulling down. Gravity is a positive force. It's pulling down in the positive direction. Tension's negative, so we'll do that. And then MA. The A is the same for both of the objects. The rope doesn't stretch and they travel the same distance in the same amount of time. So we'll just get rid of the subscripting for both of the acceleration terms and simplify. In the horizontal, not in the horizontal, in the direction of the ramp, parallel to the ramp, the X direction here, we see that we have a positive pull up the ramp coming from tension and a negative pull down the ramp coming from the force of gravity. So we'll go ahead and write that in here. Positive tension minus MAG sine theta is equal to MA times A there. And I should put an A here, and then I forgot to have the M sub B right there. It's important. Sorry, it's a little hard to see. Let me put that different color. M sub B and then M sub A right here. There we go. I keep switching the case on my subscripts, so let's just do capital casing so we don't confuse it with acceleration. All right, there we go. Looks good. Okay. Now we've kind of done the heavy lifting. The most critical piece in the beginning is just to get the directions of the forces right, the signs right, so you don't make a sign error here in our equations. Let's double check that. Tension is up, that's positive. Gravity down the ramp is negative, so we have the minus sign there. Don't forget kind of what we're doing. Let me just draw this out one more time. For the force of gravity, that's mg, and then we've got our components, and this is that mg sine theta component right there. That's theta as well. So nice review of the free body diagram there. Okay, or partial free body diagram. I'm not drawing the whole thing quite yet. All right, now we can solve. So pause the video if you haven't done this yet and solve the rest of this and see what you come up with. But then importantly, try to interpret what you're seeing. Do some what I like to call extreme thinking. Try some test cases and see if it makes sense. Try some test cases for different values for MA and MB. Oops. And theta. See if it makes sense. All right, go ahead. Okay, well, here's the result. So I'm just solving the math now, and then we'll interpret the results. So here's my equation from object A from Newton's second law. Here's my equation from object B, Newton's second law. I decided to solve for the tension over here using object A. Then I plugged that into the same expression for tension over here because it's the same tension throughout. Single rope, and then we just do all the math. Don't make a sign error, get all your subscripts right, pay attention to details, and when you do that and you factor things out, you'll see down here you get the acceleration is equal to this expression. So now that you see this, try to interpret it. Maybe you got this, maybe you didn't, but regardless, go into it and let's do some test cases, some extreme thinking. So for example, we can do something like, why don't we start with very shallow angle. Then maybe a very steep angle. So we're kind of varying the angle. Then we can think about making MB very, very big compared to MA. Or do the reverse, make MA way bigger than MB. What about a case where the acceleration is equal to 0? How could that be possible? What would that imply? So go ahead, pause the video, and try to go through each one of these steps, and then we'll take a look. All right, well, the first thing you should notice is that if we have a really shallow angle, it starts to approach what's called the modified Atwood machine that we saw when we first studied these things. So there's really no angle here. Theta is equal to 0. So if theta is equal to 0, this term here, mg sine theta, mag sine theta, that cancels out. And that turns into an expression where we only have the mass, the hanging mass here, times g divided by the sum of the masses. And that's exactly what we had before from that result. We had the hanging mass times g and then the sum of the masses here for the modified Atwood machine. So that checks well. Now if the angle approaches 90 degrees, that's essentially like this, the regular Atwood machine. And in that result, we had this expression here, a subtraction up top between the masses, and the sine of 90 degrees is what we would be plugging in for the angle if it was the steepest it could be, and sine of 90 is 1. So that would just make sine of theta here a 1, and now we have the mbg minus mag up on top, just like we saw before. So we can put some check marks by these cases. They make total sense, so we're probably on the right track. Now the next two to realize is just varying the mass, and so we can see that let's say MB, whatever, MB was much greater than MA. What would that mean? How could we transform our equation? So let's just write it real quick again so we can manipulate it here. Okay. Well, if MB was a lot larger than MA, like way larger, then we would expect that essentially this is irrelevant. It would be a really small number. So we could basically cross that out. And then we would also expect that this is a really small number compared to the mass right next to it with the addition. So you just end up with MBG over MB. Those would cancel, and you'd get an acceleration of positive g, which would make sense. It would just mean that the hanging mass here is accelerating down with an acceleration of the gravitational field strength. And it's positive, right, because down was positive and up was negative. So that checks out, and then the reverse would be true. We could plug that one in, and actually let's do that one next. Let me get another slide up. All right, so for this one, if mass A is a lot larger, we can effectively ignore mass B, these terms here. So we can just cross those out, and we get something a little bit more interesting. We get minus MA g sine theta divided by MA. Masses cancel out, which is cool. And we get minus g sine theta. Let's interpret what this means. Go back here. We draw our Atwood machine on an angle again, real quick. Okay, so basically we're saying like this is really tiny, doesn't matter at all. So we would expect this system to rotate in the negative direction, and the mass should be going, the mass on the incline right here should be accelerating down the ramp parallel to the ramp. And so this mass is doing that. It would be accelerating in the negative x direction down the ramp, and the amount of acceleration it would have would be g sine theta, but you have to have that minus sign there to agree with our convention that down the ramp is negative. So that actually checks out and makes total sense as well. We've seen that before with an inclined plane with just a single block on a frictionless inclined plane. The acceleration down the incline was g sine theta, and then you put a minus sign out in front depending on how your coordinate system is. So that checks out. That looks really good. Finally, we could ask the question, what angle would need, what would happen if we had no acceleration of the system at all? What would that mean, right? Well, there's two possibilities. We said it before in the beginning of this video. Either the system's at rest, or interestingly, it's just moving at a constant velocity, either clockwise or counterclockwise. Let's just consider the situation where they're at rest. It doesn't really matter. But if they're at rest, the velocity is constant, meaning it's always 0, 0, 0, 0, 0, and we can apply that now. So go ahead and give it a shot if you didn't do it before, and then we'll take a look. All right, so our acceleration is equal to 0. Some quick free body diagrams. We'd see that the tension pulling up on the hanging block is balanced out by gravitational force, or the weight of the hanging block. And then on the inclined plane, that block, we can see here, let me make sure I just draw the angle theta, that we have three forces: normal, gravity, and tension. But importantly, this is the key, that this downward pull coming from the parallel component of the force of gravity to that ramp, that downward pull down the ramp is totally balanced out by this up the ramp pull from tension. So therefore, that means that the tension force here at this moment in time when the forces are balanced is equal to MAg sine theta. And that's going to happen at this particular angle here. And let's solve for it. So how would we do that? Well, we just got to plug in. So 0, that's our acceleration, is equal to MBG minus MAg sine theta divided by MA plus MB. When you bring over the denominator and multiply that by 0, that's going to just be 0, so you can effectively just get rid of that. And then you can see what happens. We just solve. I'll do this right down here. So we get mb, the mass of b times g is equal to the mass of a, g sine theta. This is now looking really interesting. And notice what cancels out. Very surprising. Gravitational field strength cancels out here. And then we can solve for our answer. So when we do that, let's see, I'll do that up here, running out of space down below. Sine of theta would equal mb over ma. So we get an expression like this, and your first instinct should be to check it and see if it makes sense. What is it saying? Well, I don't know, do some test cases and see if it works. So what if the two things are equal? Mass of b is equal to mass of a. What would that mean about the expression here? Well, this would imply mathematically that the sine of theta would equal mb over mb, or just 1. When does that occur? Well, that occurs at an angle of 90 degrees. So this would say that if you wanted to balance the system and the masses were equal, well, then you'd have to do that with the angle of 90 degrees. And that totally makes sense. That's just this. So now we have MA and MB equaling each other with a 90-degree angle, which is just vertical straight up. It's basically no incline at all, or no point in having an inclined plane, because it's just this Atwood machine. And so that looks to check out perfectly fine. What we also see here is that sine of theta just goes up to 1 at a maximum, right? So you can't have mass B, MB cannot be greater than MA if you want to balance it. Because if MB were larger than MA, then the ratio of MB to MA would always be greater than 1, and you can't have sine of theta greater than 1. So that's kind of cool as well. We're starting to see, okay, well, if we wanted to balance the situation, we better make mass B to be less than mass A, and then we can find the correct angle based on the masses when we take the inverse sine. So to find the angle, of course, you do the inverse sine like this of MB over MA like that. And you'd be able to get it, and you'd find the critical angle, which is really, really cool. All right, so take a step back. Notice what we've done. We first reviewed Newton's laws and just made sure we understood the main concepts of what was important there, but then we saw this problem that took almost everything that we've learned in this unit, kind of combined it into one system. We went methodically through the process of the system, defining a coordinate system, identifying objects under analysis, identifying the forces, drawing free body diagrams, thinking about balanced forces versus unbalanced forces, writing down the second law, thinking about the direction of each force that's exerted on the objects, getting the signs right, getting the subscripts right, double checking our equations, and then mathematically manipulating the equations using algebra and trigonometry, and then finally getting to a result all in variables, and then looking at the result and saying, does it make any sense, by changing around some of the parameters and thinking about how the system would respond to certain changes here. You can see how amazing this process is, because it generates new knowledge that you didn't have before about the system, and you're just doing it in this very logical kind of fashion that stem right out of Newton's laws in this really cool way. All right, now I took you to some pretty cool advanced thinking here, I guess, with kind of interpreting all the different types of limiting cases that we could see here. But this is the type of thinking you should be able to do in terms of analyzing your result and understanding if it makes sense at all. Now here's another problem if you want to stick around and try this one too. A scenario you've never seen before. And what I'm going to do is throw in a new thing we've learned about friction and see if you can apply everything correctly. So we have a platform here, and it's accelerating up. Here's like some rod that's connected to the platform, and I'm telling you that this whole thing, this whole platform with the mass on it as well, is accelerating up at 2g, or 20 meters per second squared would be the numerical value, but we'll just leave it in terms of g, so 2g. So if this dot were the platform, you'd see the platform go and just go up while speeding up. All right, that's what's happening to the platform. All right, now while that's happening, there's a mass that's on the platform, and it has been given some initial velocity here to the right. But there's friction on the platform. So eventually it's going to slow down and come to a stop. It won't reach the end of the platform because of just, I'm telling you that, right? So this velocity is low enough so it doesn't reach the end of the platform. All right, so the question is, how far does the block slide, D here, in terms of the initial velocity, the coefficient of kinetic friction, G, and M at most? You may not see all 4 of these variables in your solution, but you cannot have any other variables other than what you see in this list in your solution. All right, so take a step back, look at this problem, and before you get intimidated by it, just realize you can break it down into steps. You have this procedure. Remember what it is: coordinate system, object under analysis, identify the forces, Newton's law, get some equations, keep going, get the signs right, etc., etc. All right, so rely upon that structure. Maybe reread through the document, the concept of force that you've seen before. That outlines that entire process and structure, and then come at this problem and see if you can solve it all on your own. And if you get down to the right answer here, that's really, really good. I'll give you one hint. You are going to need a kinematic equation from our unit on kinematics to get to the final result here. All right, that's one little hint. So, all right, give it a shot, and then we'll take a look together quickly. Go ahead. All right, let's take a look. The object under analysis is the block, and the forces on the block, well, we have the platform that's pushing up on the block. We have the force of gravity that's pulling down on the block, and then we have this kinetic force of friction on the block that's pushing to the left. Remember, there's absolutely nothing pushing with a force to the right on this block. In the past, this block was given some initial velocity. We don't know why or care. We just know that when we start our analysis, it is moving to the right when we begin. All right, so that's the first thing to note. Second thing to note is to think about the forces being balanced or unbalanced. In the horizontal direction, well, there's only one force. It's the force of friction to the left. So the forces have to be unbalanced here. All right, so we should expect unbalanced forces here. So we will have a horizontal acceleration. And then in the vertical direction, this one may or may not be tricky for you, it just depends. But you need to realize that the forces are definitely unbalanced in the vertical direction, and that's because there is acceleration. The platform and the block are both accelerating up at 2g, so we need to make sure we apply that. All right, let's keep going with the math. So over here, we can write down, therefore, that we have a force of friction, kinetic friction, and that's going to equal max. And then over here in the vertical, we have I'll call it just the normal force. It's the force of the platform on the block, which is a surface, so it's a normal force. And then we have a downward pull of the force of gravity. I'm just going to blindly add them before taking care of signs, which I'll do in a second. All right, now the kinetic friction force, importantly, we know, and I'll just kind of write this down here, the force of friction kinetic is equal to mu, the coefficient of kinetic friction, times the normal force. So we can plug that in over here. However, we just got to watch out a little bit and make sure we get the signs right. Think about it. Maybe pause the video, go through each sign. Which way is the friction force pointing on this block? To the left or to the right? And then does this make sense over here? All right, well, if you thought about it, it's pointing to the left, the friction force. So whatever happens over here on this part of the equation needs to be a negative number at the end of the day. The coefficient of friction mu k is always a positive number, so we don't get a negative sign there. And the normal force is pointing up, which is in the positive direction, so we don't get a negative sign there. So we have to manually come in here, actually put a minus sign out in front. Nice little sign check. All right. Now let me actually go to a new slide and just kind of clean this up so we have some more space to work through the algebra. But I want you to think about now, what would you plug in here for this normal force. That's the next step in this problem. Think about it, see if you can figure it out, and then we'll take a look. All right, now what I'm about to do is going to totally be wrong. So don't try to do this or remember this, but I want to see if you can figure out why it is wrong. An important skill oftentimes when doing physics, because oftentimes you'll do something wrong and you're going to need to figure it out. So let me show you what's wrong. Everything's right so far, but a student comes along and looks at this and says, oh, I've seen the normal force before. It's always equal to mg, or the weight of the object. And so they decide to do something like this. Why is that wrong? Pause the video, write it out in a sentence. This is very wrong in this particular problem, but can you articulate why? Go ahead, give it a shot. All right, well, hopefully you figured it out. And the reason why this can occur often with students when first learning physics is a tendency to want to apply exact procedures and routines seen before in other problems to a brand new problem that is slightly different because the context has been changed a little bit here. All right, so you need to let the equations, the principles, the concepts guide your thinking, not the step-by-step you might have done before in a particular problem. Okay, so let's let that guide our thinking, and the answer is staring at you right over here on the right-hand side. In the vertical direction. There's the information that we would need in order to do this. So let's go ahead and plug in and see what happens over here. All right. So we can solve for the normal force over on the vertical. We know gravity is down, pulling down, and so we would have minus mg. And then what is our acceleration value? Well, it's parameterized in terms of the gravitational field strength, g, and it's 2g. So we'll plug that in. Just about there. Now the normal force can easily be seen to be equal to an mg plus a 2mg. And lo and behold, we have a normal force of 3 times the weight of the block, or 3mg. Where have we seen this before? Well, you should be shouting out, oh, this is the elevator problem. This is somebody standing on a scale, and we're reading the value on the scale. Yeah, it's really the same idea here. It's just now we're kind of like showing it in a different way with a platform, and there's friction, etc., right? There's always connections between problems, even if they're not exactly the same problem. Now we see why we're totally wrong. And we remember that any time that we need to find the, let me just cross this out before I forget. Anytime we need to do something with friction, we have to figure out the normal force. And we've done that here. Great. Notice how we got the information from the vertical direction. Nobody told us to do that. But we have a good habit of writing down Newton's second law in both horizontal and vertical and just seeing what happens and seeing where the math takes you. Kind of have to sometimes just kind of let go and let the math move, and the concepts of physics help you move forward in the problem. All right, so we continue along, and now we can, let me just rewrite it like this first. And now we'll plug in, so we get minus mu k times 3mg is equal to ma x. Awesome. What happens next? An amazing thing happens next, and it's that the mass cancels out. And then we come in and we solve. All right, so I've done that here, and you can clearly see, hopefully, that we can find our acceleration in the horizontal direction in terms of some of the parameters that we needed. And we get minus 3 mu kg. Check it, make sure the sign is correct. The acceleration we should expect is in the negative direction. The block is slowing down while moving to the right, so opposite signs of velocity, and acceleration means slowing down. And then we can see that would make sense here. G is always positive, mu k is always positive, leading us with a negative acceleration. Now finally, the problem asked for how far this object slid, the sliding distance. We've done all this work, but we haven't even gotten to the final result yet. Now we need to take a step back. How are we going to do that? How far does it go, right? Well, you don't see anything to do with distance in Newton's laws, right? It is a way to calculate acceleration, but now, since you've studied kinematics, you know how key the acceleration is, because if we know that, we can then predict how far things go and how fast they're moving at later moments in time. So let's apply that now. All right, I've just drawn like a real simplified picture where we can see that this thing is sliding to the right a distance d. It's not moving at the final point, but it is moving with some initial velocity vi to begin with. We know the acceleration value, and we know that as long as this acceleration is constant, which it is, mu doesn't change and g doesn't change and 3 certainly doesn't change, then we can apply the equations of motion. The only question is, well, which one? Well, we don't have anything to do with time, and we want to figure out how far this thing slides. So let's write down the third equation of motion and just see what happens. So the final velocity in the x direction squared is the initial velocity in the x direction squared plus 2a times delta x. And we basically have it. Delta x here is going to be our sliding distance d. Really, it's our displacement, but we're just moving in a straight line, so they're equivalent here. And we can plug in and solve for it. We know our final velocity will be equal to 0. And our initial velocity we're just calling vi, so we'll write that. So 0 is equal to vi squared plus 2. Now we'll plug in for our acceleration, minus 3 mu kg times, I'll turn delta x into d now, just to kind of parameterize it in terms of the problem variables. And we can see the signs are going to work out perfectly here. This minus sign, when we bring this whole other term over to the other side, after we do the multiplication with the number 2, of course, it's going to turn into a positive sign. So we'll get 6 mu kg times d is equal to the initial velocity squared. And I think you can clean it up from here, put a little line here, and we'll solve for our final result. So the sliding distance d is the initial velocity squared, well, that's interesting, divided by 6 mu kg. We put a box around that, and you know the next step, right? Does it make any sense at all? So pause the video and pick your own limiting cases, your own extreme thinking. What were the things about this system in the beginning in the setup, right? And if you manipulate those things or you change those things, do the results for the sliding distance make sense? Pause the video, do some thinking in that way. All right, I've listed a few of the cases off the top of my head. Number one is kind of like my favorite one. You can imagine that we just had a way to take away all of the friction, and you have this like really long platform or something like that. If there's no friction at all, well, then mu becomes 0, and anything divided by 0 approaches infinity here, and so the block would just keep sliding and it would go an infinite distance, assuming you had some like infinite platform. In all likelihood, it would fall off the platform, of course, but that's a totally different problem. But it's making sense. Likewise, if the gravity was much larger than it usually is here, you can see how the distance would be smaller, and that should make sense because, you know, if gravity was stronger, it would pull down harder on that block, and it would kind of the weight of the block would push it more into the grooves of the platform with friction, and there would be more resistance there. There'd be a stronger force of friction, and it would not end up going as far because of that. There would be a much larger acceleration value that would slow us down and not allow us to go as far. There was a larger friction force. So that makes sense. And then the initial velocity, that obviously should make sense to you. If it is a faster initial velocity, it would slide a lot farther. But interestingly, knowing about proportional reasoning, you can extract relationships now, right? You can look at this at even a much higher level and say, oh, that's cool. The distance is proportional to the square of the initial velocity. Now you can easily compare two scenarios. Maybe you've got this scenario where you start at speed v, here's the platform, and then another scenario totally identical with the platform, but this one comes along and we say, well, now this guy gets to start with an initial velocity of twice as much. Initial velocity, what would happen? Well, immediately you see that this one travels 4 times as far because of the squared relationship, unlocking kind of the secrets immediately to you to this totally unknown system that you've never seen before, but you figured all this out, which is cool. Awesome. And of course, you could play around with these other variables. We have some inverse relationships here with the distance and the friction coefficient, and then gravity, of course, etc. Okay, so take a step back and look at all of the knowledge that we have extracted just by using fundamental concepts and principles out of both of these systems, and how you can kind of keep like you're like pulling back the layers of an onion, if you will, over and over and over again, just by doing what the physics and the math say to do, and just keep pushing with your thinking and asking questions to yourself as you're doing that process. And you just really generate all this new interesting knowledge. It's pretty fun when you get the hang of it, and you're able to kind of do this quickly. Um, so great stuff. Hope that helped you just kind of review the process on some things that you've never seen before at a pretty challenging difficulty level. And that'll help, give you success with eventually mastering these ideas. All right, take care, and we'll see you next time.